Okay, so this section is 1.5. It's all about combinatorics, which we did a little bit of in finite math. Just as a warning, Bobby caught a mouse like 10 minutes ago and it got away and now it's somewhere in my apartment. So if you hear me squeal, you know what happened. So combinatorics is a branch of mathematics where we find interesting things to count. So for example, how many ways could we arrange 6 people around a table? Or how many ways can a poker player get a pair in a 5-card poker hand? These would be interesting things that combinatorics folks, we call them number theorists, would like to count. So the first part of combinatorics is the multiplication principle. We did go over this in finite math. So suppose an activity can be divided into t successive steps, okay? Assume the first step can be done in n sub 1 ways and the second step can be done in n sub 2 ways. And we do that for every single one of the t steps. That's what this part is saying. Then the entire activity can be done in n times 1 sub 1 times n times 2 times n sub t ways, okay? So let's work through a few examples so we get a nice little refresher. So I already included the answers in these ones. So how many different outfits consisting of a coat, hat, and scarf can be chosen from 2 scarves, 3 hats, and 2 coats? So I would take 2 coats times our 3 choices for hats times our 2 choices for scarves, and I get 12 possible outfits. An exam contains 5 true or false questions. How many ways can the exam be completed? So you have 2 choices for each question, right? You have a choice of either true or false. So that's going to be 2 times 2 times 2 times 2 times 2, 5 times, right? Because there are 5 questions on the exam. All right. If you can elect a club president and a vice president in 506 ways, how many members does your club have? I did this one wrong. I didn't read this question. Let's try this again. So let's look at example 3. If you can elect a club vice president and vice president in 506 ways, how many members does your club have? Well, I would need to set it up like this. I don't know how many members my club has, but I know it has that many choice for president. And if you're president, you can't also be vice president, although with this political climate, who knows? So typically, we would take x minus 1, right? Because I've got one less choice for vice president if I already picked my president. That's going to be 506. Now we need to think way back to college algebra. I'm going to go ahead and distribute this x, so I get that x squared minus x equals 506. What I want to do is set this equal to 0 by moving 506 over here. So I'm going to subtract 506 from both sides. Because then I can factor. And I want to know what are the factors of negative 506 that add up to negative 1. Well, that's going to be negative 23 times 22. And if you wanted to figure that out, you could just start by making a nice little factor tree. Totally up to you. But that's how I'd start. And keep going. So that means I can rewrite this as x minus 23 times x plus 22 equals 0. Then I can set each of these equal to 0. So I have x equal minus 23 equals 0, so x equals 23. And I have x plus 22 equals 0, so x equals negative 22. I can't have a club with negative 22 members, so it's going to be 23. And we could check our work by seeing that 23 times 2 does indeed add up to 506. So let's solve a few examples on our own. So, suppose a license plate consists of 3 letters and 3 digits. How many different license plates are there possible? Well, I've got to choose 3 letters. There are 26 letters in the alphabet, so I can pick any 3. And duplicates are allowed, right? I could have a license plate that's AAA 000. That's not the most exciting license plate, but it's a license plate. I then have 10 choices for digits. I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, not 10, 9, right? And that gives me 10 fingers because we start counting with 0. So I've got 10 times 10 times 10. And this is going to be a big number, right? This is why they do license plate this way. So I get 17,576,000. Next, how many ways could I draw 3 cards from a standard deck if when we draw a card we don't replace it? So that means for my first card I've got 52 choices, but if I've taken 1 card away, for my second choice I have 51 choices. And then for my third choice, I've taken out 2, so I've got 50 choices. That gives me 132,600. Next, how many ways could I draw 3 cards from a deck if I did replace them? Okay, so that'd be 52. I draw a card, I put it back, so my second choice is also out of 52, and my third choice is also out of 52. So I'd get 140,608 possible ways to select 3 cards with replacement. Suppose we flip a coin 5 times and are recording this. Flip a coin 5 times and record the string if it's heads or tails. How many different strings are possible? How many different choices could I have? So I've got 2 choices for my first, right? 2 choices for my second, 2 for my third, fourth, and fifth. That gives me 2 to the 5th, which is 32. So I have 32 different possible strings, okay? Now, how many strings would have exactly 1 head? This is something we have to think about. Well, there are 5 different places that I could have a head, right? So I could either have a head in the first place, or I could have a head in the second place, or the third, or the fourth, or the 5th. So there are only 5 possible choices with exactly 1 head. The next question is different. It's how many strings have at least 1 head? Well, the number of strings with at least 1 head means I could have many heads. I could just have 1 head. I could have 2 heads. I could have 3, 4, or 5. So what I really need to know is how many strings have no heads is the option, right? Well, the only string with no heads would be all tails. So that's just 1, right? 1 with no heads. So if I take my whole sample size minus 1, which is the one with only tails, I'm going to get 31, and that tells me there are 31 elements have at least 1 head. This last question is, in how many strings is the second element a head and the fourth a tail? So I have my first choice, then I have a head, then I have my third coin flip, and then I have a tail, and then I have my 5th coin flip. So I have 2 choices for my first entry, 2 for my second, and 2 for my third, right? Because it doesn't say what our first, second, or our first, third, or 5th choice would be. So that gives me 2 to the 3rd, which is 8. So there are 8 possible choices where the second element is a head and the 4th is a tail. Okay. In the last one, it says, in how many strings does a head never follow a tail? This is a good way to sketch it out. Okay. So it could be all tails, right? If I had all tails, then a head would never follow a tail. I could have one head and then the rest tails. I could have two heads and then the rest tails, right? I couldn't have head, tail, and then another head. That wouldn't work for what we're trying to do. So let's keep going. I could have 3 heads and then 2 tails. I could have 4 heads and then 1 tail, or I could have all heads. So there are six possible ways in which a head could never follow a tail.